Okay, we are going to discussing about counters. Okay. In the previous class, we have seen that registers, right? And also we have seen counters, some part of the counters. So counters, basically, we have seen that it may be a synchronous counter, asynchronous counter, it doesn't matter. We have discussed about the up counter. Exclusively, this is a asynchronous counter. And we have also seen the down counter also. And the circuit can perform both is called up-down counter also. We have seen up-down counter. Okay, fine. Generally, from the counter onwards, we should say that we would like to represent the circuit. The circuits are called asynchronous circuits. Sorry, sequential circuits. Sequential circuits. So whatever the counter that we would like to design, that counter can be treated as a sequential circuit. Whatever the counter that we would like to design, that can be called as a sequential circuit. Now, as we all of you know that what is the sequential circuit is all about, it has got a combinational block, right? It has a combinational block, and it has got a memory block. Okay, memory. So therefore, we have to apply the input here. So this input is called primary input, and we will get the primary output, and we'll take some part of the output and connect it here, and this will be the present state of the system. So this generally, as soon as we apply a clock signal, the primary input will be applied to the combinational circuit. At that time, whatever the output is there, two outputs that we'll have, the one is the primary output, the second one is called next state output. Okay, it is called next state output. So this is the representation. It is useful. This type of circuits are called sequential circuits. Any digital circuit can be represented in the form of a sequential circuits, provided if you want to have a memory element. Okay, that means if you want to store the if you say that the output is completely not only depending upon the present input, whatever the previous history of the input, then obviously we have to go for sequential circuit. Okay, the counters are such type of sequential circuit, because for example, if the count value q is equal, for example, 0 0 0, for example, so when the moment if I'm applying the clock signal, this count value must be incremented by 1 plus 1. That means it involves the previous value. That means we have to add the previous value to the previous value. To the previous value, we have to add plus 1 to this. Agreed? So that means we need to have a previous value. So therefore it is obvious question is that it's a good practice is that the counter can be a simple example of a sequential circuit. Okay, the sequential circuit follows the nature. It is actually a function of present input and present state of the system. Okay, fine. Now let us design, for example, this is the system. For example, 2 is the one count, for example, then 5, then 1, then 7, then 4, then 3, then again 0, then it again 0, and come back to the 2, for example. So this is the counting sequence that I want to design. This is the counting sequence. What does it mean? For example, let's start with logic 0, for example. And then it has to count second, it has to count 5, it has to count 1, next 7, next 4, next 3, something like this. I want to count the sequence, right? So for what we have seen, we have seen that 0 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6, 6 to 7. Something like this we have done and come back to the original position. So this is called a simple normal sequence of counting. Okay, that means we are going in the increment order, or either we can go for the decrement order also. Either we can go this side or this side also. It is possible to have that one. If you go clockwise direction, then it is called up counting. If you go for the anti-clockwise direction, it is a down counting, right? So this type of sequential circuit does not have any problem for us. It won't make problem level. We can do it very easily. But whereas the circuit something like this has got some problem. Okay, that means it is not possible to apply the q is equal to q plus 1. For example, if this is the q, if you want to get this 5, it cannot be q plus 1. It can be q plus 4. But again, we have to increment it by decremented by 1. Okay, therefore the q minus 1. So the logic is not applicable here. The q plus 1 concept is not applicable. So therefore, such type of situations are demanding for sequential representation of the system. Then how can we do this one? Okay, so so this is also called as a state diagram. State diagram. It is also called as state diagram. So from logic 0 to logic 2, the count to 0 to count to 2, count 2 to 5, 5 to 0, 1, 1 to 7, 7 to 4, 7 to 3, something like that. Now the question is that how do we write a Verilog program to describe this behavior? Okay. First of all, the state what represents this state diagram? That's an important one. What represents the state diagram? Therefore, as I mentioned that these are called states, right? These are called states. So the count value, we can call it as the count value, or the count number we can call it as a state. We can call it as a state of a system, or digital system. Okay. So this count value will changes to the new count. This state value changes to a new count value, provided we have to apply a clock signal, right? So by applying the clock signal only, so the 2 value will become 5. Again, we have to apply a clock signal, then this value come back to the 1. Again, we have to apply a clock like this. Each and every clock signal, this has to move. Okay, fine. That means, see here. So the moment the clock dependency on which factor it is depending upon, the clock is meant for a memory. Agreed? The clock is meant for a memory. For example, the 2 is the present state. For example, 2 is the state that we have got. And we will go to by applying the clock signal, this value come back here. And that means what is happening here? This is the next state. This could be the present state, right? So therefore, what is the input for this memory element? Can you observe here? What is the input for the memory element? The input is actually the next state. What is the output here now? The present state. Agreed? Therefore, what we can observe that, so the moment if you apply a clock signal, the next state will be connected as assigned as a present state. Okay, so therefore this is what the memory is all about. The question is that what is the size of this memory? For example, as I mentioned that, for example, we are there in the second state. Then again come back to the combinational circuit, come back here at this 2. Now this value is going here again by applying the clock, and it will become 5, for example. Then it will come back here. So like this rotation will takes place. So as simply we can understand that whatever the next state that we have, that will be assigned to the present state. Fine. Okay. So the question is that what is the size of the memory? That is decided by the maximum count value. That is decided by the maximum count. What is the maximum count here now? You observe 7 is the maximum count. 7 means how many number of bits are required? The minimum number of bits, 3 bits, right? 3 bits. 3 bits are required for this. So that means that 3 bits means how many flip-flops are required? 3 flip-flops are required. That's how we have to decide the number of so this is how we have to decide the number of, okay, this is also not good. This is called maximum count. This is called maximum count. Okay. So the maximum count will decide the minimum number of bits. That minimum number of bits decides the number of flip-flops. So it is a 3 flip-flop memory element. It is a 3 flip-flop. That means here we will have 3-bit size input and we will get a 3-bit size output. Agreed? I hope you understand the concept. Understood the concept, right? Okay, fine. Now, so this is the one point that we should know. Now, so what is that? What exactly meaning of this state? State represents the content available in the memory. It's a very, very important note. State represents the content in the memory. Okay. Okay, fine. Now we have a counter. So sorry, we have a combinational block. We have a combinational block. And we have combinational block. So as we have mentioned that what is the input for this memory? So this is the one only. Do we have any extra signal to the clock signal, extra inputs to the counter? No, counter requires only the clock input. That's all, nothing else. So even though it is a sequential circuit, in this particular counter application, we don't require this primary input. We don't require this primary input, right? So therefore, without primary input, the combinational circuit we have to design, and it will also produces the output. It also produces an output, okay, and that output is connected to this one. Of course, we would like to take a output is also Q here. What is the size of this one? Again, you should understand that the 3 inputs are connected to the combinational block and 3 outputs are taken from the combinational block, and that is also again connected to this one. So therefore, this is what a simple sequential circuit that resembles that is required for a counter. Okay, so as you have to understand that the primary input may be applicable for some sequential circuit, may not be applicable. Okay, so this counter doesn't require any extra primary input signal. Therefore, we can design the counter something like this. Okay, so as soon as we are applying the, for example, I'm telling you, for example, the content in the memory is, for example, 0, 0, 0. 3 zeros are there. Okay, I'll take it outside. For example, I have the content of the flip-flops are, for example, 0, 0, 0. That means 0 is the present state. Just to apply a clock signal here, what will happen here? This clock will go here. So this content will be transferred here and do some manipulations in the combinational circuit and produce the 5 is my present state. Then it will be generated the 5 here. Okay, then this becomes 5. That means 1, 0, 1 will be the 5 will be added into the memory element. Now again, you apply another clock here, for example. Then this 5 will be manipulated in the combinational circuit and it will produce, what is the next one? No, sorry, 0 tarvata 2 ravasindi 2. It is not 2. 0, 1, 0. Okay, please understand this concept. Okay, so initial concept in man kavalsindi, as we mentioned that we have 0. Next, it will be manipulated in the combinational circuit and it will produce 2 is output, and it will changes to 2 here, and 2 will be manipulated in the combinational circuit and it will changes to 5 and yeah, 5. Yeah, I'm talking about exactly from this point of view, and this 5 is manipulated here, and again it will be changes to 1, something like this. It will be generated the sequence and we are taking the output at this point. Okay, so therefore this is simply a two blocks are available in the circuit, right? What we observe that we have two blocks. One block is a combinational block. The next block is a memory block, right? So we would like to write a program for this one. How to write a program here now? See, we'll start something like this. I will write it quickly. Module. Okay, so counter. Here is what other things are there? Clock signal, and for the time being, yeah, I would like to write also RST also, RST, and Q also. The inputs are clock, RST, and output is register data type 3 down to 0 of 2 down to 0 kada? So 2 bits are required, therefore it is 2 down to 0 of Q, right? Now put a 0. So I would like to write a memory element first of all. Okay, so the memory element can be written by simply a negative edge or positive edge rather than positive edge clock, comma, positive edge reset. This is what happening for the memory element. Agreed? So here we have a positive edge reset is required. So I'm sorry. This is the positive edge of RST is also required for us. Okay. Okay. So as I mentioned that it is simply a memory element. Okay. So 3 inputs sequential. We have a 3 inputs here. We have a 3 outputs here. That the transaction can be takes place based on the clock and reset. So let me call this is the next state. This is called the present state, right? So therefore, as soon as the clock is available, the next state will be assigned to the present state, right? So therefore, we can start here is the begin. Begin and end. If RST is true, what will happen? The content of the flip-flops must be equal to 0. Q is equal to 3 bit of all zeros. Fine. So I have initialized. Else, what has to happen? Anyone? Let me call next state is NS. Next state is equal to present state. Sorry, I'm extremely sorry. The output of the memory element is present state, right? PS, present state I'm writing as PS is equal to ENS. Okay, so this is how I need to write. So what are the outputs here now? PS and Q are the outputs. But Q I have written somehow, but PS and NS didn't mention anything here. So it is internal to the circuit, right? As you observe that these are all internal to the circuit. NS and PS are internal to the circuit. Therefore, I would like to write here is register 2 down to 0 of PS, comma, NS. Agreed? Okay. So therefore, one part is completed. What is the next one? Next one is a combinational block. So here is the matter. Here is the combinational block. So this combinational block requires present state. It will produce the present state. So apply the present state, and we have to generate the Q output signal. We have to generate the Q output signal. Okay, or we can say that this is the next state also. Okay, Q can be connected to the again to the next state. Of course, we can do it also. Okay, now let us write. So what is the inside of this block? That's an important one, right? So this is what an important one. So this block will be there inside of the combinational circuit. Inside of the combinational circuit. So as soon as the present state is something, okay, sorry. Please wait for 2 minutes, 2 to 3 minutes. I'll complete it. Okay, so This is what inside of the combinational circuit. So what is the here? We are applying the present state. We are getting the output Q, right? So that means if you are, for example, we write a logic is something like this. For example, you are in this position, for example. Yeah, wait. For example, you are in the zeroth state. Okay. By applying the clock signal, we have to go to the 1. Sorry, 2. After that, we have to go to the 5. After that, we have to go to 1. After that, we have to go to, I think that is 3, 7. 7. Next 4. Next 3. Next, again, come back to 0. So this is the sequence we have to follow, right? So therefore, here also, I'm going to use either the n number of ways that I can implement this state diagram, but simplest method is using the always statement. Here also, I'm going to use always statement for the second block. But this always statement output completely depending upon the present state. As you agree with me, the present state. Okay, so that means what is the sensitivity list for this this particular block? This combinational block came out from the input change అయితే output change వస్తుంది అంతే కదా. So when there is a change in present state, then only the change of the Q will be observed. That's what I can write. Here I am writing case statement. So this is the newest one. I'm writing here begin end. ఇక్కడ ఏం చేస్తా అంటే just I'm going to use case statement. Case the present state. That's what I would like to write. If the present state is equal to so and so, if the present state is equal to, for example, you are there in the 3-bit of all zeros. You are there in this particular state, for example. Okay. So where it has to go, what is the Q value? What is the Q value? Q will be assigned by, if you are there in the present state, what is the next state? Q will be the next state only here. The Q will be 3-bit of 0, 1, 0. The 2 is the second state. Okay. So what is the way? So I'm writing here also. 3 decimal of 0 I'm writing. So decimal representation I'm writing. Q is equal to 3 decimal of 2. That I can write instead of writing 3 bits, something like this. Therefore, I will follow that notation only. So 3 decimal of miri state lo unnaru anukondi. Where you have to go? You have to go to the 5th state. Q is equal 3D of 5th state. For example, 3D of 5th state lo unnaru anukondi meeru. Next, where you have to go? 3D of 1 state alala. If you're there in the 3D of 1 state, for example, then Q will be 3D of 7. If 3D of 7 you are there, then next state will be 3D of what is the 3D of 3D of 4. Okay, if 3D of 4 you are there, then next state could be 3D of what is the 3D of 4? The 3. Okay. Next, last one is 3D of 3 if you are there, and Q is equal to 3D of 0. That's it. Okay. Therefore, we can write end case here. So, and of course, the default statement also I need to write. Better we need to write the default also. So default for all other cases, the Q is equal to 3D of 0 only we would like to write. Okay. So somehow we have defined the Q value. Fine. There is no doubt at all. But how do we define the next state? How do we define the next state? Normally Q is nothing but the next state only. So I would like to write the Q is equal to something like this. Assign. I would like to write assign. Okay. Okay. Where I should write assign statement within state Q I have written. Okay. I think it is better to write the next state. Okay, next state, right? Okay, we'd like to write here is assigned. Assign q is the next state is equal to, sorry, next state is equal to q. State is equal to, whenever the q is changes, then automatically next state will be defined there. Okay, I think, yeah, we have done it. I think it's not the good idea. The best idea I will write here. Please forgive me. This I would like to change here in this way. Uh, the q is assigned by the next state. Okay, here all the q are replaced with the next states only. Just to replace all these with the next state only, a small modification is required. I will tell you why we are using this next state, something like this. Here we write next state, and next state. If you want to write the q is outside, then I should remove this one also, and I would like to write yeah, here it is not a problem. Yeah, here is not a state. Yeah, present state. The PS is equal to 3 bit of all zeros, and now this is right. Nested is. So this is what the program it is. Please try to implement this program in your Vivado and see is there any problem. We will see that from whether we are getting the same output or not. We will see in the lab session. Okay, so the clarification of this code, of course I have done almost thing, but a little bit I have changed it according to the data notations for that. But logic is something like this only. For the memory element, simply a D flip-flop. For the combinational block, we have to use the state diagram. So the state diagram we have to write by using the case statement. Okay, so this part we would like to implement in the tomorrow's lab, and I will discuss about some points related to this one. Okay, we stop here today, and we will see the things in the next class. Okay, yeah. One point is required here. All of you please do one thing. Just wait for some time. Sir, are you there?
Yes, sir.
Just a second.